In this lesson, we're going to start to look at compound interest. So by the end of the lesson, we should be able to know the difference between simple interest, which is not really used by financial institutions, and compound interest, which is much more commonly used. And we should be able to calculate the present value and the future value of a lump sum investment compounded over different periods of time. So lump sum means a one-time investment. So we're going to invest $1,000 one time and watch it grow, or we're going to borrow $1,000 one time and see how much we're going to owe. Later on, we're going to look at an annuity, which is a repeated payment over and over and over again. So let's say we're saving $100 every single month over and over again. So we're going to start off with lump sum, and then we're going to move on to annuities. Before we start calculating compound interest, we need to understand what is interest. So interest is the cost of borrowing money. So if we borrow money, we're going to pay interest. And if we lend money, we'll earn that interest. And interest is always quoted as a percent. So it's never as a lump sum. So anytime you borrow money, you'll be quoted an interest rate as a percent. So examples of times we would pay interest is if we are borrowing money for a car or for a mortgage. That means that we're borrowing money against a house. On a credit card, when we use that, we're borrowing somebody's money and then we're going to pay them back, or a line of credit. But if we lend our money or invest in certain investments, we can earn interest. So an example of that would be a savings account. So if we put our money in a savings account, the bank will offer to pay us interest. A very small little bit of interest, but still interest. Bonds would be another example. That's lending money to a company where they're going to pay us regular payments. And investments. Now, this is not really interest. This is more a rate of return, or a rate of growth is even better. So let's just add growth. So investments like mutual funds, ETFs, and stocks, they're not going to pay us interest, but they're going to grow in value, similar to a savings account growing in value or a bond growing in value. So you might have heard of the power of compounding. So to illustrate the power of compounding, we're going to look at simple interest, how that's calculated, on compound interest. And what we're going to notice is that compounding is going to increase our value exponentially, while simple interest is just going to increase it in a linear fashion. So here's the example we're going to work with. If you lend $1,000 to somebody and ask for 8% annual interest rate, which is huge, by the way, how much will they owe you in 20 years? So we're going to figure it out using simple interest, and then we're going to figure out using compound interest. Okay, so I just threw together a quick chart to help us organize our calculations. So on the left we have year, and then we have interest earned, and we have total value. So we know that in year 0, so when we first lent the money, our investment, we can consider this an investment because we're going to earn money. So we're not going to earn any interest in at the beginning of the investment. So our first starting value in year 0 is going to be 1,000. And then after 1 year has passed, we're going to earn 8% on $1,000. We're going to is $1,000 times 8%, which is $80. So that means our total value is $1,080. So in simple interest, the next year we're going to earn the exact same amount of interest again. So the interest is calculated on the principal, which is the original amount that we invested. So again, it's going to be $1,000 times 0.08, and so we're going to earn another $80. So that means, which means we're going to have $1,160 at the end of the second year. So this is going to continue on and on. So in our third year, we're going to earn another $80. And we'll have 1,240, and et cetera, et cetera. So now we can calculate how much our investment is going to be worth in 20 years, because we know that in 20 years, we're going to make $80. That is $80 per year, so $80 20 times, plus we're owed back our original amount that we loaned, which is $1,000. Which means the person that borrowed from us is actually going to have to give us back $2,600, which is a pretty good rate of return for us. So if we were to come up with an equation to figure out what our total value would be, that 20 was just the number of years that we were investing. So if we call that N, we could make an equation where we say that N, our $80 was our interest, and that was just a constant value, so we can just use I to represent interest, and then we're going to add back our principal value. So our interest is a known number, in this case it's 80. Our principal is a known number, and this guy n is going to change depending on the number of years. So this is just a linear equation where this is our rate of change and this is our initial value, or this is our slope and this is our y-intercept. So now let's take a look at how compound interest works. So let's start to fill in our chart. We know that in year 0, we know that the amount of interest we'll make is 0 and our beginning value is 1,000. So let's take a look at year 1. So just like simple interest, we're going to take the amount, the current value of the investment, and we're going to multiply it by 0.08. We know that's going to be $80. So our total value is 1,080. So in simple interest, we just continually calculate the interest by multiplying the interest rate by the principal amount, the initial amount that we invested. In compound interest, our interest is always going to be calculated based on the total value of our investment. And our total value of our investment is always going to be increasing because it's going to include the interest that we earned in the last period. So that means that in year 2, the interest that we earned, if it's compounded, is going to be calculated based on the current value, which is 1,080. We're going to multiply that by 8%. And we'll get $86.40. So it doesn't seem like a lot more, but it is more. So we're going to earn $6.40 more interest this period. So now our total investment is going to be $1,166.40. So in year 3, our interest is going to change again. It's going to be based on $1,166.40. We're going to multiply that by 0.8, our interest rate. And we're going to get $93.31. So here we can see it's really growing. We were making an annual interest amount of $80. Now we're making $93. So it's increasing exponentially because we keep multiplying by 0.08. So our total value is going to be $1,259.71. So now we can sort of see the pattern here. We're going to take our principal amount, which is 1,000, and we're going to keep multiplying it by 0.08. But we also have to add back the original amount. And so we need to change this 0.08 to 1.08 because we have to include that 1,000. And then we're going to multiply it n number of times depending on the number of years. So what we're doing is we're taking 1,000, we continue multiplying it by 0.8, 0.8, 0.8. What we're really doing is multiplying by 1.08. That's how we get this total value here. And we're going to keep on doing that for 20 years. So our calculation will look like 1,000 times 1.08 power of 20. So before you put in your calculator, you can estimate it. Because these two examples were calculated with the same numbers, they should have about the same value. When you put it into your calculator, you're going to get $4,660.96. And if you take a look at what we calculated with simple interest, that's a huge difference. That's almost a $2,000 difference, which goes to show you that compound interest is going to increase much faster than simple interest. And the reason is just take a look at the math of it. This is an exponential equation. We know it's going to look something like this, while a linear equation is just going to increase by the same amount every single time. So here we've got an exponential equation that looks like this. And here we have a linear equation that looks like this. So you can understand mathematically why compound interest would be in our best interest in this case because we're earning this interest. So if we were to come up with an equation to represent compound interest, we have $1,000. That was just our principal amount. So we can call it P. Another way to remember that is our present value, what we borrowed in the present. We're going to times it by 1 plus our interest rate, and all to the power of n, and that's going to give us our final value. So we're going to call that A. So if you think about the implications of compound interest, the higher the rate that we're multiplying by, the faster this thing is going to increase. So if we are lending somebody money, compound interest is going to work in our favor because it's going to increase in value so quickly, we're going to get all that money. But can you imagine in a situation where we are borrowing money at a high interest rate, such as a credit card, then we can see that if we don't pay that credit card debt down, it's going to continue increasing exponentially in value, which could get us into a lot of trouble. Total value. So now that we understand the basics of compound interest, we can work it out without a table of values because we understand how it works. So here is this formula that we actually derived. We have A is equal to P times 1 plus I to the power of N. So we've already gone through what each of these means, but let's do it again quickly. So A stands for the accumulated value. So it's the total value at the end of an investment's term. So however long it is that we're compounding our interest. So it's also called the future value. It's the value that it's going to be worth in the future. P is its value right now. Like right now we invested $1,000. So P can be considered the principal, the initial amount that we invested or the initial amount we borrowed. Another way to think of it is what's the value today? So today that amount was worth $1,000. Later on it was worth closer to $6,000. And then we know I is our interest rate per compounding period. We're going to talk about that in a second. It's expressed as a decimal, not a percent. And then N is our number of compounding periods. So that means the length of time that it's going to be left to increase in value. So let's take a look at our first example. It says George decides to take a night school course at a local university and borrows $1,200 from the bank to pay for the course. The bank charges him interest at a rate of 5.25% per A stands for per annum, which stands for per year. So write that down if you need to remember. Compounded annually. Compounded annually means that the bank is going to charge him interest on an annual basis, which is the same example that we did previously. It doesn't always have to occur this way, and we're going to look at other examples later on. It says he plans to pay back the money in 4 years. So he's borrowing one time $1,200, which means that we can use our equation that we have above. So just a reminder, that equation is A is equal to P times 1 plus I to the power of N. So the first thing that's easiest to write down is what variables do we have? So are we given A? Are we given P? Are we given I? And are we given N? So it says, how much money will Anthony owe after 4 years? So if he's going to owe it at the end of the 4 years, that means we don't know the future value, the accumulated amount. The present value, or the principal, today he's borrowing $1,200. So that's what the principal or the present value is. Our interest rate is 5.25%. So we got to change that into a decimal. So it's going to be 0.0525. Okay, and the number of compounding periods. How many times is the bank going to charge him interest? Well, they are charging him interest on an annual basis, and he's going to pay the money back in 4 years, which means he's going to be charged interest 4 different times. So we can plug everything into our equation. We don't know our accumulated value. We do know the present value or the principal. And then we have 1 plus 0.0525, all to the power of 4. And if we put that in our calculator, that's going to give us an accumulated value of $1,472.55. So this is the amount that he has to pay the bank at the end of the 4 years. So the next question says, how much interest did he actually pay for this loan? So just think about this logically. There's no fancy calculation. He originally borrowed only $1,200, and in the end, he has to pay $1,472.55. So whatever the difference between these two numbers are, that must be the amount of interest that he was actually paid. So the amount of interest is just going to be, we're going to take that, our accumulated amount, and take away our principal value or our present value. So the total interest is going to be $1,472.55. Subtract 1,200. And we'll get $272.55. So that is his cost of borrowing money. So this is the amount of interest. So dollars of interest that he's actually going to pay over those 4 years. So you can ask yourself, is it worth it? Is it worth me having this money now and I have to pay $272 for it? So the next question is similar. It piggybacks off of George's question because it says Janaya takes out a loan from the same bank as George. So they charge her the same interest, which is 5.25 per annum. So that means per year, but pays $2,000 back at the end of the loan's term, which is 5 years. So because this is the same bank and this is the same loan, let's assume that's also compounded annually. We don't know how to do semi-annually yet. We're going to learn that in a second. So they're charging us 5.25% annually, compounded annually, and she pays $2,000 back at the end of the loan's term. So the question is, how much did she borrow originally? So if we write out our equation, first of all, it says that she took out a loan from the same bank, which means that was a one-time payment or a one-time like principal amount, which means that we can use our equation that we have. So our accumulated amount is P times 1 plus I to the power of N. Let's fill in what do we know now. So our A, our P, our I, and our N. So it says that she pays $2,000 back at the end of the loan's term, which means that this must be our future value, which she pays at the end of the story, which is our accumulated value, $2,000. So A is now $2,000. What we don't know is how much did she borrow originally. So how much did she borrow at the beginning of the story? Sorry, so let's put a question mark beside P. So we don't know how much she borrowed at the beginning. What principal did she actually invest or borrow? Our interest rate is going to be the same as our previous example, so it's going to be 0.525. And this time she's borrowing it for a total of 5 years, which means that interest is going to be applied 5 times to the loan. So let's fill in the information that we have now. So we have our A value, so we're going to fill in our A. A is $2,000. We're looking for our P. 1 plus our interest rate is going to be 1.0525 to the power of 5. So now we have to get our present value or our principal amount on its own. So we're going to divide by 1.0525 to the power of 5. Don't deal with the decimal until the very, very end so we get the most precise answer as possible. Dealing with these tiny, tiny numbers will make a big difference if we press equals on our calculator in the middle of a problem versus at the end of a problem. So that's going to cancel out, and we're going to be left with our principal value is $1,548.53. So that's what we got as our present value or our principal value. Does this number make sense? If she owes $2,000 and it's gaining interest, that means at the beginning of the story she must have borrowed less than that. So this number is less than $2,000. It's not hugely different, which means that we're probably on the right track. So in our calculation, it shows that she must have originally borrowed $1,548.53. It was compounded annually at this interest rate for 5 years, and we got $2,000. So this is how much she borrowed originally. Compounding periods can change depending on the type of loan or investment that you make. So we've only been dealing with examples where interest is calculated or compounded annually, so at the end of every single year. But it can be compounded in the middle of the year, so semi-annually. It can be compounded quarterly. It just depends on the investment. So for example, a mortgage, that's a loan against a house. Those are typically compounded monthly, which means that every single month our interest is being charged to us. A credit card is another type of loan, and that's actually compounded daily, which means that the interest or the credit card company charges us on a daily basis interest. So the more times a year that interest is charged towards us, the faster our total value is going to increase. So if we are earning this money, that's going to work in our favor. But if we are paying this money, that's going to work in our detriment. So let's just take a look at these words, annually, semi-annually, etc., and take a look at what it means for the number of compounding periods per year. So how many times interest is going to be calculated or charged per year, what it's going to do to our interest rate, and what it's going to do to our N. So annually means that there's one compounding period per year. So we've got one. Interest is going to be charged one time, which means our I value is going to stay exactly what it is, and our N value is just going to be the total number of years that we have this invested. If an investment is compounded semi-annually, semi means 2, so it's going to be interest is going to be charged to us twice a year, which means we're always quoted our interest rate per annum per year, which means that if we're going to get charged this interest for the whole year, but if we're going to get charged it 2 times, that means we got to take our interest rate and divide it by 2. So for example, if our interest rate was something enormous like 10%, the bank is going to charge us 10% for the whole year. Well, if they're charging us 2 times a year, it wouldn't make sense to charge us 10% 2 times. We would take 10%, divide that by 2, and we would be charged 5% 2 times, which would make 10. So our N value is going to be our number of years, and we're going to multiply that by 2, What that means is, let's say that something is being compounded semi-annually for, let's say, 4 years. Well, we're going to be charged 4 years 2 times. So we want to multiply it by 2 because it's semi-annually. And the pattern is going to continue this way. So quarterly, if it's compounded quarterly, that means it's 4 times per year. We're going to take the interest rate that will be quoted per year. We got to divide that by 4. And that's where we're going to be charged every single period. Our end values, we're going to take the number of years that it's invested and multiply it by 4. So if it invested for 3 years, we're going to be charged 4 times per year, which will make 3 times 4, which is 12 times. Monthly means 12 times per year. We're going to take our interest rate divided by 12. And our N is going to be our number of years times 12 monthly. Okay, then we have weekly. Well, there's 52 weeks in a year. So our number of compounding periods per year is 52. We're going to take our interest rate divided by 52. And the number of years, let's say it's 2, well, that's going to be times 52 weeks. And finally, we have our daily compounding. This is the most expensive it can get, and credit cards use this. So that means that we're going to be charged interest 365 times per year. So our interest rate is going to be super tiny. We're going to divide it by 365. And our N, which is the number of times interest is earned or charged, is going to be the number of years times 365. Some other words that we might come across are bi-weekly, that means every 2 weeks, and semi-monthly, which means twice a month. So let's work on some final examples to make sure we understand this. So in example 4, we're just going to do some quick, simple calculations. So it says calculate the amount earned at the end of the term. So that means we're looking for our A value. So we need our A value. $300 is invested, so that's going to be our P value. At 15% per annum, slash A means per annum, so that means per year, compounded daily for 2 years. So we've got to come up with our I value and our N value. So I is the rate of interest per compounding period. So our rate of interest is 15% per A, which means per annum per year. So 15% per year, that means our interest rate is 0.15, but it's compounded daily, which means we're not going to be charged 15% every single day. We got to figure out what we're going to be charged every single day. So we got to take that thing and divide it by 365. So that means our actual interest rate is 0 point, and then we have 3 zeros, 1, 2, 3, and let's take at least 2 more numbers. So 4, 1. It would be ideal if we took more, but that's okay. So our actual interest rate that we're going to apply every single period is 0.0041, and our N is the number of times we're going to apply this interest rate. So we are investing for 2 years, but it's compounded daily, which means we're going to invest 2 years 365 times, which is going to work out to 730 times interest. 730 times interest is going to be applied. So if we put this all into our equation, we have our A value we don't know, our P value is 300 times 1.00041, all to the power of 730. And we get an accumulated value of $404.65, which is reasonable when you take a look at what we originally invested, which is $300. So try the next guy on your own and check back to make sure you've got the right answer. So if you did it right, our principal value is $7,000. Our interest rate is 2% because we've got to divide that 8 by 4. Our number of compounding periods is 20, and when you put everything all together, we should get $10,401.63. So let's quickly finish up the last few questions. So this one says Jamal's parents want to have $15,000 in his education savings plan by the time he is 17 years old. How much should they invest when he is born so that they can achieve this goal if they know they can get a return of 4.5% per annum compounded monthly? So they found this sort of magic investment vehicle that is going to pay or get a compounded rate of return of 4.5%, and it's going to be compounded monthly. So in this magic investment vehicle, we know that they said that they're only going to invest one time when he's born. So as long as it's one time, we can still use our trusted equation of A equals P times 1 plus I to the power of N. As soon as we've got multiple payments, repeated payments, we got to use an annuity formula, which we're going to do next. So filling it in, we have our A value, P value, I value, and N value. And once we have those, everything's sort of easy peasy from there. So it says Jamal's parents want to have $15,000 by the time he's 17 years old. But right now he's just born, which means that 15,000, that's at the end of the story. That's what they want to have in the future. That's a future value. They don't know how much they want to invest today. So they don't know the principal amount. The interest or rate of return that's going to get compounded is 0.45%, but it's compounded monthly. So we got to divide that guy by 12. Which is going to give us 0.00375. Take as many decimal points as you can, because as I said, you miss one number and your number could be like quite a few dollars off. So the number of times that their interest is going, or they're going to earn this return, is they're investing it for 17 years and it's compounded monthly. So 17 times 12, which is 204 times. So when we throw all this into our equation, we have 1500 is equal to our P value. Then we have 1.00375 all to the power of 204. We're going to divide by this guy here, 1.00375 power of 204, and divide on the other side. And we're going to be left with our P value equal to $699.00, which is really interesting. So all they have to do is invest $700, and if they invested in this account that's earning 4.5% compounded monthly for 17 years, they will have $15,000. 5 cents. Oops. Okay, so here's our final question. It says Sylvia decides to invest $500 in a GIC, Guaranteed Investment Certificate, on June 1st. She earns interest at 2% per annum, compounded annually. So that 2% is the annual rate, but we know we got to divide that thing by 2 because it's going to be charged to us twice per year. On December 1st of the same year, she decides to invest another $500. This time, she finds a GIC that earns her interest at 3% per annum compounded quarterly. How much will she have earned from both investments if both GICs mature the following December 1st? So let's quickly organize ourselves with some sort of divider. So our first investment starts on June 1st. And it's going to go until December 1st of the next year. So let's say that this is June 1st of 2018. That means it's going to mature on December 1st of 2019. And our second GIC, we're investing it on December 1st of 2018. Let's just say 2018. And then it's going to mature the next December 1st. And we'll say of 2019. So both of these guys are going to mature or stop calculating interest in the year 2019 on December 1st. We know that in this first example, she invests $500, so that's going to be our P value. So our P value is $500. We won't know our A value. She earns 2% compounded semi-annually. So we got to take that 2% and divide it by 2, so it's going to be 1%. And then our N value we're going to figure out in a second. Let's fill in the information about our second guy. Our second guy also investing $500, so our P value is $500. We don't know our A value. Our interest is 3% compounded quarterly. So our interest rate that we're going to use is 0.0075. Okay, and we'll figure out our N. So our N for the second guy is actually a little bit easier because we're investing for a year. And if it's compounded quarterly, that means that our interest is going to be charged to us 4 times. So our N is equal to 4. for our first example here, our n is a little bit trickier, but we can figure it out. So the number of months between June 1st and December 1st, well, that's just a year and a half because the number of months is just 18 months. So a couple ways we can do that. We can just think about if it's going to get compounded semi-annually. That means every 6 months. So how many 6-month periods are between here and here? And that answer is 3. Another way to think about that is the number of years from June 1st to June 1st, 2018 to December 1st, 2019 is 1.5. So we could just take 1.5 and multiply it by 2 because it's semi-annually. We also get 3. But again, a simpler way I think is just to calculate how many semi-annually periods are there. So meaning how many 6-month periods are there in between June 1st, 2018 and December 1st, 2019. And that answer is 3. So now all we have left to do is do our 2 calculations and add them together. So try the 2 calculations on your own and then check back in the video. So our first investment will be worth a whopping $515.15, and our second will be pretty much the same, $515.17. So our total is just going to be adding them together, which will be a total of $1,030.32. So that's what our 2 investments will be worth in that year and a half period of time. So really, we're just making about $30.32. So the next one just says, if both GICs were invested over the same time period, which one do you think would yield a greater return? Well, that's a little bit obvious. So let's just talk about the multiple parts of this. The first guy, that's interest rate is 2%, and the other is interest rate of 3%. So obviously this guy's going to win. But on top of that, this one's compounded semi-annually, which means we get interest charged to us twice per year. And this one's compounded quarterly, which means that it's going to grow 4 times per year. So let's say that those 2 interest rates were the same and the only difference would be its compounding periods. The one with more compounding periods is going to increase more rapidly. So this compounded quarterly would increase faster. So it's taking a look at the interest rates is obvious, but what if those interest rates were the same? Well, compounded quarterly would increase faster than interest that's compounded semi-annually.